Okay, as I was saying, lecture number 9 for cryptocurrency decal, how we can allow Bitcoin to scale and reach, become basically a global payments platform. So what is the scalability problem? There are many meanings of the word scalability, but in this context, we'll primarily be talking about the ability of a system to deal with an increased transaction volume. And to do this, we'll measure it using something called transactions per second, or TPS. This is basically the velocity of transactions through the system, and this means like in the entire Bitcoin system, how many transactions are being made over a certain period of time. We should also be considered when we talk about scalability also with blockchain size, because the blockchain is already about 106 gigabytes, and like that's quite a bit where it's like infeasible to run a node on your phone, or even like for most people wouldn't want to even store that on their laptop per se. And even if you're using like an SPV wallet, which we have talked about in the course before, that's still about 106 megabytes, which is still pretty infeasible for, like, usually you don't want to give up that much storage space on your phone. So how can we make it so more nodes can store the blockchain in the future so the size of the blockchain doesn't increase too fast? So let's go ahead and figure out what is the current max TPS of Bitcoin. So what we see here is this is a chart of average transaction size over time in the Bitcoin network. But really the key thing that we want to take from here is the average size of a Bitcoin transaction is 546.38 bytes. And using this information, doing some dimensional analysis, we can go ahead and figure out what is our maximum transactions per second. So given 546 bytes per transaction, the current maximum block size is 1 megabyte, and the expected time to next block is 10 minutes, right? Therefore, we can compute the sustained maximum transaction volume in TPS and come down to see that we have 3.2 transactions per second. And so let's see, how does this compare with other traditional payment systems? So right now, like we determined, it has a high load of about 3.2 transactions per second, and the average is about 3 transactions per second. When we gave this lecture last semester, it was actually the average was only about 2.2. So as we see, the Bitcoin blockchain is being used much faster, and we're very quickly approaching our theoretical maximum. So how does this compare to other systems? Well, PayPal on average handles 150 transactions per second, but it's designed to handle a maximum of 450 transactions per second. So Bitcoin has a long way to go before it can even match PayPal. But Visa on average handles 2,000 transactions per second and is designed to have a high load maximum of 56,000 transactions per second. So when we're discussing Bitcoin scalability, if we come at it with the goal of making it a global payment system, we shouldn't just be thinking about how can we increase the Bitcoin TPS over the next few years in order to deal with the current demand. We should be thinking about how can we compete with other global payment systems. So even if we do like linear increases, that's really not getting us to where we want to go, which is competing with systems like Visa. So from our previous slide, we figured out these are the 3 things that go into finding our maximum transactions per second, right? So essentially, this isolates the 3 variables that we have to play with. We can either play with the size of transactions, the size of blocks, or the block creation rate, right? So let's go ahead and start off with a naive solution. Let's just change the block creation rate. All we have to do is increase the speed of blocks. It's a pretty easy solution. All we have to do for that is just decrease the difficulty of the mining problem, and then blocks will be found at a faster rate. So for this lecture, we've gone through about half the course now, and so I thought it would be interesting to allow you guys to try to come up with any cons of all the proposals that we're talking about, based on your knowledge that you've gotten from the past few, from the high level, low level knowledge you guys have of the Bitcoin blockchain. So let's go ahead and take like 30 seconds and discuss with your neighbor about what do you think are some flaws to this solution, and then we can reconvene. Okay. Anyone have any potential cons that they see with doing this? I heard a few right answers already. Like, you mentioned something?
Increase orphan blocks.
Yeah. If the difficulty of the problem becomes easier, it's more likely for two people to find the same problem, the solution at the same time, which will increase orphan blocks. And that also, increasing orphan blocks also, and that means that it's easier for an attacker to do double strand attacks. Anyone else? Yeah.
It would make like the supply of bitcoins like run out faster.
Yeah, so that's another issue. It will mess up like the block reward halving, and will end up running out of Bitcoin a lot sooner. Yep. So some of the cons are the propagation time is a higher ratio of the block time. So once you create a block, it takes time to distribute your solution across the network. And basically, when the propagation time becomes a larger percentage of the ratio of the entire 10-minute block time, it makes it more beneficial to withhold blocks, and it also makes it more likely for the miner who found the previous block to find the next block. Because if, let's say, the propagation time is 20% of the entire block time, that the miner who starts off with that block has an extra like 20% of the time and is more likely to find the solution. There's more block orphaning, as you mentioned, messes up block reward halving, more frequent forks. It's less likely to be accepted as a solution than just increasing the block size, because changing the block speed is a bit more fundamental to the protocol, because it does affect a lot of other things, such as like halving and stuff like that, and difficulty. And so it's much easier just to change one parameter of the maximum block size than it is to change this more embedded part of the protocol. So just from a political and technical feasibility standpoint, there's really no purpose of doing this. And it would make the blockchain storage size increase faster, because now you'll have a new one megabyte added every 5 minutes instead of every 10 minutes. And one might think like, oh, if we're having blocks come faster, and like how we're always supposed to wait for 6 confirmations, oh, that means we'll have to wait half the time. But in reality, the security of the blockchain is not coming from just the number of confirmations. It comes from how difficult those confirmations were. So if you have the difficulty, then you just have to now wait for 12 confirmations for an equivalent amount of security as you would for 6 confirmations with 10-minute block times. But wait, this may not be that naive of a solution, because here's Vitalik Buterin, who's the creator of Ethereum, proposing exactly that and being just completely ignored. I mean, this Reddit post is more purely academic and was a protest against segregated witness. But if you actually read through his proposal, it's actually a pretty good idea, and it could work in theory without needing a hard fork. But the point of this post was more just to poke ideas at the absurd, complicated soft forks. But if anyone wants to talk to me about this interesting idea afterwards, you can. And also, keep in mind, Ethereum does have 17-second block times, but it does a lot of it has something called the Ghost Protocol, which allows it to do a lot of interesting things. It basically rewards orphaned blocks. These orphaned blocks are called uncles, and if you accidentally find an orphaned block, you still get a smaller percentage of the block reward. And so this is how Ethereum manages to have 17-second block times. And it's pretty important for Ethereum to have 17-second block times, because on Ethereum, as we mentioned, there's smart contracts running, and you'd want a smart contract to update state at a much more faster rate than every 10 minutes to do one step. And Vitalik has this like really, really great blog post comparing soft and fast block times and why Ethereum decided to go with fast block times. Anyway, let's talk more about what are the more current and reasonable implementations on the Bitcoin blockchain. So the most obvious one is increasing the block size. This is actually Satoshi Nakamoto on the Bitcoin Talk forums. He's actually mentioned this directly. This is a quote from him. He's basically said, at a certain amount of time, after a certain number of blocks, we can just go ahead and increase the block size. So what are the pros of increasing the block size? It's a pretty easy implementation. It's just one parameter that needs to be changed, and it's all you have to do is get all the miners to agree. And if anyone's been following Bitcoin politics for the last like year, you'll know why there's like that many asterisks on like getting all miners to agree. And then it will also lessen transaction fees, which is good if you're a user. So yeah, anyone have any ideas of what are some cons of just increasing the block size? Yeah.
If you increase the block size, isn't that going to increase the time it takes to find all the transactions to put and therefore increase the block processing time?
You could have a block that's not completely filled with transactions. So that's why like right now, like I said, blocks don't necessarily have to be filled. These are like the max size of the blocks. Yeah.
It doesn't solve the storage problem.
Yeah, it will increase the storage much faster. Anything else? Think about perhaps when it comes to like propagation and stuff like that, more like network level stuff. Okay, I'll go ahead. So one, it would require a hard fork, but whatever. Like I have my own opinions on why hard forks are okay. It will lessen transaction fees, which I mean, it's bad if you're the miner. The size increases very fast, and it's also sort of a slippery slope because the argument is, let's say we just double the block size now, then we could just double it later and double it and double it and double it until like there's no end to it, and then the blockchain storage size will increase like a lot, and just like doing it once, it leads to this slippery slope. It'll have longer propagation times because if you have a larger block, it takes more time to propagate that data across the network. It's a one-time linear capacity increase. It's only a temporary fix. So like, hey, our maximum TPS is 3.2. If we double the block size, oh great, we're at 6.4. Well, Visa is still handling 56,000 per second. And there's also a large transaction attack where there's this one, a few years ago, there was this one block that had a transaction that was almost like 1 megabyte in size, that this block contained only this one transaction, and it took 25 seconds just to validate this block. And so it's been shown that if you have a block that's nearly 2 megabytes in size, so close to filling up an entire 2 megabyte block, it will take over 10 minutes to validate the transaction, and that will cause like major problems right there. So that's one like a new attack vector that comes from increasing the block size.
How could someone exploit that?
How could someone exploit that? So basically, I think what happened here was there was a miner who was doing this as a protest and purposely created a transaction that was really big and hard to verify and put it in the block just to show that. But what do you mean by how could someone exploit that?
How could someone use that for their own personal monetary gain?
Oh, because if it's taking everyone else a long time to verify, if it's taking everyone else, you can't start mining the next block until you verify the previous block, right? And so if everyone's taking 10 minutes to verify the previous block, he's spending all that time already working on mining the next block. And so he'll find the next block before everyone else has even finished verifying, and so he'll basically control the entire system because he'll always be a step ahead. Yeah.
Wait, why wouldn't it just work in the large blocks?
Yeah, so yes, that's an option. If all the miners agree that like, hey, this guy is just like trolling, and they could just choose to ignore this block. So what are some of the proposals that have come along with the idea of increasing the block size? We have Bitcoin Classic, which recommends increasing the block size to 2 megabytes. XT, which brought it up to 8 megabytes and doubles it every 2 years. As you can see, that's a very fast increase in storage size. BIP 103, which has an increase of 17.7% annually until 2063. They have some math explaining why those numbers, but I think the most interesting one and the one that has the most traction and controversy around it right now is one called Bitcoin Unlimited. Bitcoin Unlimited, basically their intention is to create, allow it so that the block size is decided by supply and demand to a transaction fee market. Basically what they believe is that it removes a point of central control in the Bitcoin protocol. They say that the 1 megabyte block size or any block size is ultimately arbitrary, and they want to make it easier for miners to like adjust the block size as needed in order to match transaction like throughput velocity at any given time. And also you can allow this free market with the transaction fees that'll basically come to equilibrium and decide a block size and transaction fee. Yeah.
So basically, someone may supply like a large block size, but they won't be allowed to demand that because of latency.
Because so what happens is if you have a smaller block size, right, the transaction fees go up because if there's a lot of transactions, more people are trying to fight to get their transactions into the next block, right? So then what will happen is like the size of the block will increase, allowing the transaction fees to go down. And so if the transaction fees are too high, users are just not going to use it. And so you're kind of just letting the market decide. You have to have a lot of trust in like the free market for this to work. A little bit about how that actually works is it adds 3 new parameters. You have a maximum generation size, which is basically the size of the blocks at so if you're the miner, you have these 3 new parameters. And this is the size of the blocks that you are going to produce. So by default, it's 1 megabyte. So that way when it actually forks, it's just a continuation of Bitcoin. So basically, I would be producing at 1 megabyte. The excessive block size is the maximum size that a miner will accept. At default, it's 16 megabytes. But let's say mine was set at 2 megabytes, right? If someone sends me a 2 megabyte block, I will accept it as valid and continue and start working on it. But what happens if someone sends me a 4 megabyte block when my excessive block size was 2 megabytes? I'll just completely ignore it and still keep working on my own chain. I won't start working on their block. But what happens now won't that mean that at some point that like, if people are just resistant, they will never agree, and now you'll just have 2 chains running in parallel with people who don't accept the 4 megabyte one? What you do is there's a third parameter called excessive acceptance depth, where basically it overrules the excessive block size. And basically, if the chain that had this 4 megabyte block that I didn't originally accept reaches a length of 4 blocks longer than the one I'm working on, I'll say, fine, you know what, that chain is the true chain, and I'll switch over to that. And this basically allows it so within an hour, the blockchain will always reach some sort of equilibrium over time. The default right now is 4 blocks deep, and it also activates a period of sticky gate, where a miner will accept any size block for the next 24 hours if they were forced to switch, just so it makes it easier for the blockchain to come to equilibrium. There's also some very interesting attack vectors when introducing the sticky gate, but we can talk about that after class if anyone's interested. Okay, now another one. So if you've been keeping up with the Bitcoin news, you'll know that the big debate nowadays is Bitcoin Unlimited versus segregated witness. I'm going to say that they're not really in opposition to each other. They are both can be implemented together, but it's honestly come down to a lot of politics at this point. So what is segregated witness, though? Segregated witness is the idea that the digital signatures for each transaction take up a lot of space. This is a piece on like Max's slide from like lecture 4, but basically what we have here is in one input transaction, the script sig, the reason it's actually just dotted out is because this script sig is actually very long. It takes up almost like 50% of a transaction size. And so the idea is there's really no reason that they need to be there. We only need the script sig once for verifying the transaction, but once it's in the blockchain, we can assume that if it's deep enough in the blockchain, it was true, and no one can change it at this point. And we don't really need the signature in order to make new transactions using that as input, right? So the idea is let's go ahead and just remove those from the transaction data. So basically, we can move this to a separate add-on outside of the script pub key. And Bitcoin Core is super conservative and wanted to avoid a hard fork. So they use a lot of super hacky fixes in order to make it work with a soft fork. So what they did was basically any old node that comes, they introduced they're basically there's one kind of script that means let anyone withdraw this money. And so they basically reuse the purpose of that in order to enable segregated witness. And so any old node that now sees this a new segregated witness style transaction come in will see it as the script will mean that anyone can spend the money, and they'll think this is kind of weird because like why? But it wouldn't really matter to them because it's not really their money, so they'll go ahead and verify it anyways and accept it as a true transaction. Well, any new node will go ahead and know what to do with it properly. The caveat is that anyone, so while an old node will be able to continue to verify these transactions, if it receives the transaction, it won't be able to spend it until it updates its software. So one of the caveats about calling SegWit a soft fork is all the wallet software still has to go ahead and update to the newest protocol. So that's why they actually have, unlike most soft forks where you usually only need about 50% approval to trigger the soft fork, for a SegWit you actually need 95% approval because it's honestly only semi-soft fork. And so segregated witness enables another minor trick as well. There's a lot of people who are worried that, hey, if we take out these witnesses, there's really no, fundamentally you want to have some proof of witness data stored in the main blockchain as well. So what it does is, based off of the transaction Merkle tree, it'll create an identical segregated witness Merkle tree that mirrors the transaction tree. And then the segregated witness Merkle root will then be included as into the input field of the Coinbase transaction of that block. And basically, as such, the segregated witness Merkle root changes the transaction data of the Coinbase transaction and its transaction ID, and therefore overall influences the block header and ultimately the makeup of the blockchain. And the purpose of this is, so not all miners have to choose to store the segregated witness Merkle trees, but if any of them do choose to do so, they can go ahead and recreate that Merkle tree, find the block header, and make sure that it matches the Merkle root in the Coinbase transaction. And this is just a way of kind of like auditability if you ever want to prove in the future that, hey, a transaction in the past, all these transactions were verified. Yeah.
Is this the action in segregated witness that helps resolve the transaction permeability attack?
No, the transaction malleability attack is more of, there's a quirk in the cryptography of how you can actually change the witness data, transaction data, and still have it be valid, a valid signature. But since you can change that, it will actually go ahead and also change the Merkle root, which will cause like problems. So really the purpose of segregated witness in the first place was to solve transaction malleability. Because if you just take the witness data out of the transaction, there's nothing to modify.
And the witness data is just that super long signature.
Mm-hmm.
If you take that out, then it can't easily be tweaked.
Yeah, if you take that out, it doesn't influence the Merkle root of the transaction tree, so you can't change the value of that Merkle root and keep it valid.
So SegWit has evolved beyond that purpose.
So the original purpose was that, and solving transaction malleability is pretty important because it's an important part of allowing the Lightning Network to function, which Philip will be talking about. But at the same time, what we see is that since the signature data is about 50% of transaction sizes, if we go ahead and remove those from the block, now we have like an extra half a megabyte to fill. So now we can, in theory, put twice as many transactions in the same 1 megabyte block. So it's like a pseudo doubling of the block size without actually doubling the block size. So one of the pros of this is it's only a soft fork. It fixes transaction malleability. There's no slippery slope because once you do it once, you can't do the same thing again. It's a one-time solution. It's a one-time doubling. There's a bunch of efficiency gains and not smaller size of blockchain, but it maintains the current size of the blockchain. So we're not actually doubling the block size. It's still only adding 1 megabyte every 10 minutes. Some of the cons is it's only a one-time solution. So once again, great, we went from 3.2 to 6.4. That's not really helping in the long run. It introduces a new kind of DDoS attack. It's very complicated and ugly with over 500 lines of code. And like I said, there's a lot of very hacky solutions that go into allowing it to work. There are other ways of solving malleability that aren't as hacky and don't require this kind of convolutedness. And of course, like I said, wallets have to incorporate it. So every wallet, if you want to make a transaction, you have to update to the latest software. So finally, this is a kind of a somewhat related to segregated witness, SCHNORR multi-signatures. Basically, it's a newer cryptography that allows, instead of in a multi-signature transaction, instead of requiring the signature of every single signer in the transaction, you can combine them and only require one signature. It's pretty much, all the pros of it is it can be implemented with either soft or hard fork, clean over hard fork. The multi-signature transactions will be significantly smaller, so that will allow more transactions. There's faster verification. It allows plausible deniability for participants because now you can't tell which of the multi-signers actually did the signing. And honestly, why wasn't it implemented is basically because when Bitcoin first came out, ECDSA was the most popular algorithm just because Schnorr's is still under patent protection, but it's not anymore. So, and it's pretty much better in every way. It just needs to be implemented. So if anyone has any free time over spring break and wants to earn some extra credit, go ahead and submit the BIP to implement Schnorr's. So now what? We've basically played with all the variables we had to play with. We've changed the block creation rate, we've changed the size of transactions, and the size of blocks. And what we see is all of these have their own pros and cons, but they really only still get us to this like linear level of increase where, great, even if we bring it up, like the block size up a little bit, we'll get like 2x or 4x or 8x, but it's really nothing getting us to allow us to compare with PayPal or Visa. And also, a lot of these solutions involve increasing the size of the blockchain, which, like we said, is not sustainable because then if the blockchain becomes too big, then only like miners with really, really high storage capacities will be able to mine on Bitcoin, which will just further increase the centralization problems with Bitcoin. So, what do we do now? Simple, we just don't use the blockchain. So how do we do this? One option is something called sidechains. Sidechains are a way to scale a blockchain without using the main Bitcoin blockchain by offloading some transactions to different blockchains. So here's an idea. Basically, if you wanted to go ahead and buy your morning coffee, right? The reason we can't, like we said, the reason we can't decrease the block speed is because it reduces security to an extent, right? But because there's more orphan blocks. But really, if you're only buying your morning coffee, and like, what are the chances of someone legitimately trying to double spend on your $3 coffee, right? So why don't we go ahead and create a way for you to spend on a different blockchain only for like these smaller purposes. And the idea is you can have all these different blockchains that are used for different purposes, but you want a way to basically peg them together. And so this is like, it's called the Internet of Blockchains. And for example, the idea is that if you have your main Bitcoin blockchain, you can have this like smaller chain only designed for micropayments and what you do is you have something called two-way pegs that holds these together by basically there's a script that you have to throw your Bitcoin into and it will create cryptographic proof that you can then use to redeem coins in this new blockchain. And then it also works in the other way. You can go ahead, there's another script that you can go ahead and throw those coins into receive cryptographic proof that you can then you can use to redeem coins in the Bitcoin blockchain. And this allows two-way pegs, so you have the same essentially value that's being transferred across blockchains, but then in each blockchain you can have different features and functionalities. And this is an idea that a lot of people in the blockchain space are playing with. For example, Hyperledger is really trying to allow a system like this where you can have public blockchains and private blockchains and everyone just working together in this grand internet of blockchains. And yeah, And so now we'll go ahead and Philip will talk about the Lightning Network, which is another off-chain scaling solution.
Yeah, so previously we've been talking about on-chain scaling solutions that give us kind of linear increases. Sunny just mentioned sidechains, which give us potentially much larger increases because you can offload onto other blockchains. What I'm going to talk about next is something called Lightning Network. I'm not going to describe it yet, and we're going to kind of build up into it and establish some of the underlying concepts that we need to understand it. So before we do that, we're just going to recall some intuition about Bitcoin transactions. There's some issues with using Bitcoin as a payment system. First, there's like long delays. You know, if Alice is paying Bob for something, you know, Bob has to wait for like 6 confirmations before sending Alice the goods. If you look at the fee market right now, you're basically paying about $1 or, well, 50 cents in fees per transaction. And if you're buying like a morning coffee, that starts to get pretty expensive. So we can't really do micropayments or paying for like items of small value. So we're kind of going to conceptualize is we want Alice and Bob, you know, 2 people, to be able to make transactions between each other without having to always consult the blockchain. So instead of always making transactions on the blockchain, maybe Alice and Bob can do something so they can make transactions between each other, like maybe they make 100 transactions, and then somehow later settle up onto the blockchain. Again, kind of what we're conceptualizing is this sort of private balance sheet between Alice and Bob. So for example, maybe Alice and Bob set up this private balance sheet where Alice has 10 Bitcoin, Bob is 5 Bitcoin, and say Alice pays Bob 2 Bitcoin. And now they update their sheet, and all of a sudden Alice has 8 Bitcoin and Bob has 7 Bitcoin. And you know, maybe they can somehow update their balance sheet without having to go make an actual transaction on the blockchain. And that way they avoid the long delays and the fees and whatever else. To kind of expand on this, you know, Bitcoin allows for very simple like contracts in a way. So what we can kind of, you know, hypothesize is maybe we could like have a contract that opens up this private balance sheet. It like initializes it in some block. And then between Alice and Bob, they can make lots of transactions, you know, updating their balance sheet. And then later, they can settle up and basically redeem their balance sheet and give each other the right amount of coins. And we're going to see that this is actually, in fact, possible. And it's pretty cool. So these are actually called payment channels. So I called them like balance sheets before. In blockchain land, they're kind of called payment channels because you can make a channel between 2 people and they can send money back and forth in the channel without having to touch the rest of the blockchain. The full name for these payment channels is actually hash time-locked bidirectional payment channels, or HTLCs. If you read the Lightning Network paper, you'll see the acronym HTLC a lot, so just be aware. The hash time lock part is a implementation detail of the actual contract, which we'll see in a second. Now, before I actually go into describing how these HTLCs work, we're going to establish a bit of notation. So we have this kind of funky like box to describe transactions. So, for example, this is an incoming transaction from someone with like 10 Bitcoin signed by someone, and it's sending to Alice. So Alice can redeem this output for 10 Bitcoin if she signs it with her signature. And let's say Alice does that. She wants to send Bob 3 Bitcoin. She signs this output. This is this input. And then it's outputting to Bob with 3 Bitcoin and then 7 Bitcoin back to Alice as change. And see, Bob can redeem this output by signing it. Alice can redeem this output by signing it. Hopefully that kind of makes sense because we'll be looking at this in more detail in a second. So how we're kind of going to set up a payment channel is we're going to create a 2 of 2 multisig output. Basically, we have Alice and Bob funneling into this 2 of 2 multisig transaction. And we kind of notate the 2 of 2 multisig by having these 2 sig boxes. So in order to redeem this 10 Bitcoin output that Alice and Bob built, both Alice and Bob have to collaborate and sign the output at the same time. So in essence, it should be kind of clear that we can have this sort of, yeah? You have a question?
The payment channels, is this the side ledger that they're maintaining before they transact and settle up on the blockchain, or is this settling up on the blockchain after they? I just missed that.
Sorry, this is so whether this is on the blockchain or not on the blockchain, this is like setting up a payment channel on the blockchain. This is actually not on a separate blockchain, which is the interesting part about the Lightning Network. It's not on a separate blockchain. It's building a private balance sheet that you like set up on the blockchain, and you can modify over time, but not have to touch the blockchain, and then later redeem it.
So it's set up off the blockchain.
It's set up on the Bitcoin blockchain, but you make transactions
On the
off
side.
the just between the two parties.
And then you activate that one that you set up to settle up.
Yes, yeah. So yeah, just hope everyone's clear on this notation. We have a 2 of 2 multi-sig transaction, and it should be kind of clear if Alice and Bob are both cooperating at all times. You know, they just set up this 2 of 2 multi-sig transaction, and maybe between themselves they say like, oh, I owe you this much, you owe me this much, and they like change that however much when they make transactions, and then later they can both agree like, oh, I owe you this much now, and you owe me this much, so we can just redeem the multi-sig transaction. The issue is, of course, if one of them is cheating, Alice and Bob would have to trust each other with just a simplified construction. Instead, what we want to build is this contract that allows Alice and Bob to make these like IOU updates trustlessly, so they don't have to trust each other in order to make these updates. So the way we're going to do that is by setting up this commitment transaction. This is going to be kind of complicated, so bear with me for a second. Let's kind of step through this. So Alice creates this commitment transaction. She also creates a secret, like a random secret value, hashes that secret value and sends it to Bob. And so she creates this commitment transaction that spends from the 2 of 2 multi-signature output. She signs it and sends, in the output field, 5 Bitcoin to Alice. And this is the really difficult part. This is the hash time lock contract part. So essentially what this is saying is this will send to either Alice or Bob 5 Bitcoin. And in order to spend that, it either requires Alice's signature and Bob's secret, or Bob's signature and Bob waiting like 1,000 blocks for like a week. Now, Alice has created this transaction. She signed it. She actually gives it to Bob. So Bob now has this transaction in his memory or something. The key part is that Alice has already signed this transaction, so at any point in time, Bob can sign this transaction and it'll become a valid transaction and you can broadcast that. The key though is that the transaction is built so that it'll immediately send Alice 5 Bitcoin. So she immediately gets her money back, and then the only way that Bob can spend the second part is if he waits 1,000 blocks. Now, because Alice and Bob have traded their hash secrets, if neither of them cooperate, they just have to wait 1,000 blocks, and Bob can redeem it. Otherwise, we're going to see in a second why this secret value is useful. So Bob actually creates basically a mirror transaction where Bob is spending out of the multi-signature transaction. So he signs it, sends himself 5 Bitcoin, and has the same hash time lock contract part. So in order to spend it, it needs Bob's signature and Alice's secret, or Alice's signature and waiting 1,000 blocks. So the key here is, again, Bob creates this transaction, he signs it, he gives it to Alice. So Alice now has this transaction. All Alice needs to do is sign this transaction, and she can redeem this transaction and broadcast it to the blockchain. What happens though is that Bob just immediately gets his money back, the 5 Bitcoin, and Alice would have to wait 1,000 blocks in order to spend it. So this is kind of the commitment phase where we're building up this hash time lock contract. Now we're going to see what happens when Alice and Bob want to make a transaction and update their balance sheet. So suppose Alice is going to send Bob 1 Bitcoin. Basically, she creates another one of these contracts and just updates the values. So now she creates a contract in secret. She updates the value to be 4 Bitcoin, and the other value to be 6 Bitcoin. So both Alice. Sorry, let me backtrack a second. So when Alice and Bob want to send money between each other and update their balance sheet, they both have to create new secret values, and they basically hash these secret values and send them to the other party. So Bob has Alice's new secret value hash. Alice has Bob's new secret value hash. And again, we have this contract. So Alice has signed it. She gives this contract to Bob. Bob doesn't broadcast it yet, but he can sign it and basically redeem it, where Alice gets the 4 Bitcoin and Bob would have to wait 1,000 blocks again. The key there is the other field is redeemable by Alice if she knows Bob's new secret. So Bob basically does the exact same thing. The key part here is that in the second output, Bob can spend it if he knows Alice's new secret. And so now we basically approach the key step of this algorithm, and that is Alice and Bob both exchange their original secret values. So now Bob knows Alice's secret 1 value, and Bob knows Alice's secret 1 value, and Alice knows Bob's secret 1 value. So if we look at how Alice could potentially cheat, for example, let's say Alice has just paid Bob 1 Bitcoin in their updated balance sheet. Let's say Alice wants that 1 Bitcoin back and tries to redeem one of the old transactions that they created. In other words, the transaction had the 5 Bitcoin to Bob and the 5 Bitcoin to Alice if she waits. The key here, though, is that if Alice broadcasts this transaction, she's already signed it. Bob has Bob has already signed it. She can sign it, broadcast it to the network. Bob immediately gets his 5 Bitcoin back. Now, in order for Alice to steal the 1 Bitcoin, she would have to wait 1,000 blocks. However, in the previous step, they exchanged the secret 1 values. And so Bob now knows Alice's secret 1 value. In other words, he can now sign this output, go to the secret 1 value, and then just take all of the money in the balance sheet. So in other words, if Alice tries to renege on one of her previous payments, Bob can just overrule that because he now knows the old secret and just take all the money. So in that way, we kind of built up this balance sheet construction where at every stage they kind of commit to a new updated balance sheet, and if they try to backtrack to one of the old states, the other party can override them and take all of the money.
How does Bob know if Bob have to continually be monitoring to see if Alice is engaged in this transaction?
So that's part of the time lock. So, in order for Alice to take the 1 Bitcoin back, she would have to wait 1,000 blocks. And in that 1,000 blocks time span, Bob would have to be monitoring for this renege transaction and be able to repudiate with his secret value. Yeah, so it's kind of complicated, but hopefully this gives you some intuition. So the key part here is that Alice can have this balance sheet construction, and they don't have to trust each other. That is, it basically follows the key tenet of Bitcoin transactions is that the two parties don't have to trust each other, and they can make transactions, across global distances. And again, if one tries to cheat the other, they can show that the other one's cheating and take all of the money out of the contract. Now, of course, if both Alice and Bob are cooperating and they're not trying to cheat, they can actually just spend directly out of the multi-signature transaction. So if the final value in the balance sheet is 6 Bitcoin to Bob, 4 Bitcoin to Alice, they can just create a new transaction that sends 6 Bitcoin to Bob, 4 Bitcoin to Alice, and both sign it and everything's fine. And what the blockchain basically sees is these two transactions. Even though there might have been hundreds or thousands or tens of thousands of these balance sheet updates in the meantime, they only ever show up as two actual transactions on the blockchain. And so in that way, between two parties, these payment channels let you have like an arbitrary number of transactions while only ever using like the fees of two actual Bitcoin transactions. So the key part here is that, you know, if they're cooperating, they only have to do like two transactions, everything's fine. It's pretty easy. And it's also a really nice scalability boost because, again, they can make any number of transactions in that time. Of course, there are some issues with this simplified payment channel. You know, you can only have like these arbitrary number of transactions between the two parties. And you don't really want to be opening up like payment channels with everyone you want to transact with. Like, you know, if you're shopping on Amazon, you're not going to open a payment channel with every like Amazon merchant because you're only making like one transaction with them or two transactions or something. So what we kind of want is some way to leverage these payment channels, but, you know, assume that people only have a couple payment channels open at a time. And this kind of leads us into the Lightning Network idea, where you have a network of payment channels. If we assume these are like nodes in the network like Alice, Bob, Fred, Charlie, let's suppose Alice wants to pay Charlie over these payment channels, over the Lightning Network. However, Alice isn't directly connected to Charlie. Alice doesn't have a payment channel open directly between herself and Charlie. However, she is connected by some number of intermediary payment channels. And it actually turns out it's possible to create this like chain of payment channels where you can trustlessly send from Alice to Charlie all through payment channels and never touching the blockchain. And this is the key innovation of the Lightning Network, is that you can basically trustlessly send transactions over a network of payment channels. If you're interested in reading more, I suggest you look at their white paper. It's pretty interesting. So some conclusion we can draw about this Lightning Network construction is that if you assume there's enough like capital in this Lightning Network set of payment channels, you can basically make like instantaneous payments across the entire Lightning Network with the security of the underlying blockchain. And what's really cool is that you actually kind of change your mental view of the blockchain as not as the payment system, but actually as an arbiter. So the only time you interact with the blockchain is to either create payment channels or to dispute if someone tries to cheat. And so it turns out, you know, with Bitcoin, you have like maybe 3 TPS or 6 TPS or whatever if you do some incremental changes. But with the Lightning Network, you're really only limited by like communication overhead over like an internet network. And as you should know, that's fairly low by comparison. So you can literally have like tens of thousands or, you know, hundreds of thousands of TPS over like something like the Lightning Network. And so instead of getting these incremental linear changes, you get like by changing the architecture or our model of how we do payments, we can get huge orders of magnitude increase in like transactions per second. Of course, there are some issues. The nodes in this like center of the Lightning Network would probably have to have large amounts of capital locked up into these payment channels, especially if they're connected with several neighboring nodes. And there's a fairly significant centralization force where it requires less capital if there are less nodes in the network. So it kind of gives us a tendency towards this sort of hub and spoke topology, where you have like maybe a singular large bank in the center with connections to some like large brokers who then have connections to the actual like people. And from Bitcoin's kind of decentralized value, that's maybe not so good. But yeah, so hopefully that should give you an idea of how the Lightning Network works. And to summarize a bit, you know, Bitcoin and other similar blockchains definitely have a scalability issue. You know, we've talked about some of these sort of linear one-time increases, like the SegWit or block size increase. But really, what we need if we want to reach sort of global scale transactions is architectural changes that give us orders of magnitude increase, something like the Lightning Network or sidechains. And again, to give an overview, we have like the block size capacity increase, SegWit, whatever. So we've kind of gone over time. Just for next time, we have a homework assignment. So on Piazza, we'd like you to make a post and argue about some topic in the scalability debate. I think Sunny can explain this.
Yeah, essentially, go ahead and out of the scalability solutions we offered, what are your opinions on what provides a short-term solution? What are some long-term solutions? Is scalability even something we should care about? Because I've heard arguments saying that hey, Bitcoin isn't supposed to be a global payment system. It's just a store of value. And so, any thoughts that you have, just a short paragraph about what are your thoughts on the scalability debate?
Also, can we get people up in front to get a picture for the air display?
Get free money if you do.
Get more free money.